Welcome everyone to today's HPL seminar. Today we'll be hearing from Andy Pohl. Andy is currently a PhD student here at the University of Calgary, advised by Dr. Reid Ferber. Andy began his undergraduate studies at the University of Alberta and transferred to University of Otago in New Zealand. He holds bachelor's degrees in mathematics and applied science and sports technology. As a PhD student in kinesiology, Andy explores the use of Bayesian inference for measurement error propagation in common biomechanical analyses. Outside of academia, Andy was a semi-pro Nordic skier and has also worked as a senior analyst at High Performance Sport New Zealand. In that role, he leveraged machine learning, natural language processing, and statistical analysis to identify patterns of performance and action for elite New Zealand and international athletes. The ultimate goal was to maximize the performance of New Zealand athletes at the Olympic Games. In his research, Andy is interested in how we can use the mathematics of probability and statistical modeling to describe and understand data generation and modeling processes in biomechanics. His proudest accomplishment is contributing his statistical analyses expertise to publications across numerous groups in the kinesiology department at Calgary. When he isn't behind a computer screen, Andy loves all things winter skiing. At one point, he lived in continuous winter for 8.5 years by flying between bases in Canmore, Europe, and New Zealand. Now he enjoys coaching Masters athletes and is eager for them to compete in the Masters World Cup in Canmore next week. So with that, I'll turn it over to Andy for his presentation, and then we'll have a question and answer period to follow.
All right, thanks for that introduction, Emily. I'll just try and share a screen here. Hopefully that comes through clear and everyone can hear me. That's great. So you may have gathered from the title of my talk that a lot of this presentation will be focused around statistics and statistical modeling. But to sort of present these ideas, I thought I'd focus on what may be one of the fundamental types of analyses that we perform in biomechanics, that being the estimation of the pose of the body to derive kinematic quantities, and in particular, deriving those from indirect measures, that being the location of markers placed on the body that we detect through optical motion capture. Such an analysis is quite fundamental in the field, and I'm sure you'll agree that provides the basis for understanding the likes of injury mechanisms, and also forms an integral part of more complex analyses such as inverse dynamics or musculoskeletal modeling, where we try to understand not just the way that the body is moving, but the loads that that body is being subject to or is being performed on that body. So for this talk, I've got three main outcomes. I hope to use this sort of framework of inverse kinematics to introduce the concept of probabilistic modeling and how we can use this to quantify uncertainty, and in particular the uncertainties related to the determination of kinematics from optical motion capture. In doing so, I hope to highlight the use of Bayesian inference to fit these types of models, and I'll demonstrate a couple of extensions to this modeling sort of pipeline that may help to improve our estimation. So to develop these types of models, we first need some intuition about what an inverse kinematics problem looks like, and also need to set up some notation. So I've tried to describe a problem here schematically, a planar two-dimensional inverse kinematic problem on the right-hand side of the screen. And it's these planar problems, these two-dimensional problems that I'll focus on for the majority of this talk. And near the end, I'll include some brief discussion about how we may generalize these techniques to the more complicated three-dimensional case, and some issues that may arise when we do so. But if we take note of the figure here on the right, when we perform a kinematic type of analysis or via optical motion capture, we generally start with a static trial. And this enables us to determine the local coordinate system for a number of segments that we may be trying to model, number of rigid segments. And so once we've determined those local coordinate systems, we're able to measure the position of a set of tracking markers. Here, these 4 gray dots attached to each of these sort of links in this schematic. And we can determine the position of these within the local coordinate system of each link. When we consider someone moving or capture a motion trial, what we measure are these Y's, the position of these markers in space in the global coordinate system that we establish from our optical motion capture system. And our goal is generally to estimate kinematic parameters such as maybe the translation of our segments or of our chain here, this vector R, potentially segmental angles, these thetas here that define the orientation of our segments, as well as any sort of functional quantities of interest from these parameters, such as joint angles, the relative difference between these segmental angles. What makes this problem interesting from a statistical perspective is that our measurement process, our optical motion capture systems, are by no means perfect, and there is noise inherent to the estimation and the measurement of these markers in space. Now, I've tried to highlight that here on the image on the right by including these white points here, and you can see that they are somewhat randomly distributed around where perhaps you could consider the true positions of these markers, the slightly grayer dots here are in space. And these areas generally can be classified quite broadly as coming from one of 2 sources. We can consider areas that may be well described by random processes arising from such things as converting the reflected light or the transmitted light from these markers and digitizing those to a pixel value and ultimately on to a position in space. We could also perhaps consider distortion of shape of these markers during movement as being somewhat random in nature. But then we also have systematic errors, and these errors may be considerably larger in magnitude. And a common one that we're often concerned with is something like soft tissue artifact, that being the relative motion of these markers on top of soft tissues, which move on top of the underlying rigid skeleton that we may be trying to model. And so most of the work I'm going to present today will be focused around the idea, or be targeted towards understanding these random errors, but we'll discuss what the implication of some of these systematic errors may be later on. So a traditional, sort of common approach to dealing with this error in these measurements is through optimization, in that we try to minimize the least squares error between predicted marker location. In this case, I've determined those to be, or notated those as alpha here, given from our observations Y, we try and minimize that least squares error given estimates of our parameters R in any sort of segment angles. And we can have 2 broad classes of these optimization routines. We can either consider optimizing locally on a segment by segment basis, where say we consider the 4 markers associated with this segment to estimate that, in this case being a planar problem, the 3 degrees of freedom, the translation in 2 dimensions, and the orientation of that first segment. And then we repeat this process for perhaps the second segment in our chain that we're trying to model, allowing some sort of dissociation or some dislocation here at what may be a joint, some relative movement between these 2 segments. In contrast, we can incorporate kinematic constraints and perform a global optimization type of scheme. So here, instead of modeling these 2 segments independently, I've imparted a hinge constraint at this joint here, and I incorporate that into my optimization when computing the predicted markers alpha. And as a result, I consider all 8 markers here on this chain when I'm trying to minimize this least squares error and get an estimate for these parameters. And this type of routine, these inverse kinematics routines, are quite common. They're certainly widely available in many software packages. For example, OpenSim or Visual 3D, you can perform any of these types of optimization. And these optimization solutions are fantastic in that they do minimize the effect of random errors. And if we consider global optimization, may help to also attenuate some of these systematic errors, in particular soft tissue artifacts. But fundamentally, they fail to quantify, they fail to fully eliminate that random or these random errors that are present. They simply minimize that error. They don't minimize it to zero. And as a result, we should have some uncertainty in our kinematic estimates. Now, unfortunately, if we just perform optimization in isolation, we don't really get a good conceptual understanding of what that uncertainty is. For example, while we may be reducing the least squares error between predicted and observed markers, we don't really have an intuition about what that may mean if we were to consider, say, a joint angle. And this is somewhat problematic, and a simple thought experiment can help clarify this. If we were to consider capturing the same kinematics, the same motion from, say, two measurement systems, maybe an older optical motion capture system, subject to quite a large degree of error, and perhaps a more modern system with less error, then we wouldn't expect to have the same confidence in the estimates of our kinematics provided from both of these systems. However, if we just perform optimization and look at the output in isolation without knowing the context of what system it was captured through, then we don't really have a good understanding of what that uncertainty is. And so the ultimate sort of goal or question I'll be addressing in this presentation is, how do we go about quantifying some of these uncertainties, and how can we go about modeling them? So one potential solution is to consider a probabilistic model, and that we try to describe our uncertainties within our data generating process through this notion of probability. So as an example here, if we were to consider a kinematic chain that we've sort of been looking at thus far, we would treat our observations, these y's, as realizations from a probability distribution, such as here, this multivariate normal distribution, given our known quantities, the positions in our local coordinate system, these x's, and their unknown kinematic parameters at translations or segmental angles. And we have two general types of techniques and statistics that we can use to fit this type of model to observe data, these y's, these marker locations. The first being maximum likelihood estimation, and the second being Bayesian inference. And it's this concept of Bayesian inference that I'll be focusing on today. So Bayesian approaches to statistics have interested me for some time. I was using them quite extensively when I was working at High Performance Sport New Zealand. And hence I was quite interested when I moved here to Calgary and joined Reed's lab. I was quite interested in how we may go about applying these to biomechanical types of problems. And luckily enough, I came across this article quite early on in my studies here by Todd Patake and others. And that really piqued my interest about how we could use Bayesian Bayesian inference to deal with some of these kinematics problems that we've been looking at. Fundamentally, in a Bayesian type of analysis, we not only treat our observations as being random variables, but we also consider our unknown parameters as random variables as well. And we use this notion of probability and to describe the uncertainty that we have in these parameters, in these model parameters. We have to start with what's called a prior distribution. This is a probability model which describes the uncertainty in our parameters before we observe any data. And then we look to update this prior distribution given the data that we have observed. And this updating procedure is governed through something called Bayes' rule, quite a simple law of probability. And I've tried to outline it here in this top equation. And in principle, we take a probabilistic model for our data generating process, in this case in orange. We combine it with for our prior distribution for our unknown quantities, our unknown parameters, this being our blue distributions here, a joint prior. We normalize it by this integral term down the bottom, and we end up with what's known as the posterior distribution. The distribution describing the probability of observing particular values of our unknown parameters here, in this case, our kinematics Q and unknown measurement noise sigma, given our observed markers Y and our sort of known quantities, these local positions in the local frame at X. And so defining a prior distribution is certainly a very, very key element, a critical element for performing a Bayesian analysis. And it's something that I put quite a lot of attention to in our earlier paper that was published last year, in that we examined different types of prior distributions that we could formulate for these inverse kinematics types of problems. And we looked to see what type of effects they had on our inferences. But it's not a topic I'll spend a huge amount of detail on today, beyond saying that there is a wide variety of priors we should consider or could consider, and we should spend a bit of time thinking about what those mean for analyses. And these can range from quite informative priors, if we had a lot of information about what we suspect the likely values of our parameters to be, perhaps based on an extensive body of previous literature, then we'll probably be looking to formulate what's known as an informative prior. Would be wanting to incorporate that previous literature and knowledge into the estimation and updating of parameters given the U data that we've observed in a given experiment. At the other end of the spectrum, we could consider an uninformative prior, in that we try to express complete ignorance about any particular values of these parameters. And we, again, update that ignorance upon observing data. And it's this uninformative style of prior that I'll be using for the results that I'll present today. So we were interested in seeing how our sort of traditional least squares optimization approaches compared to a Bayesian approach and a probabilistic modeling approach for these types of inverse kinematics problems. And so what we did was we simulated a 3-link model of the lower limb in a format that sort of resembled how we may perform a typical optical motion capture analysis. So we sort of assumed this type of 3-link kinematic chain, and we modeled the lengths of these links to somewhat resemble what may be sort of typical for a human. And we posed this chain to sort of, again, somewhat resemble what may be typical during the stance phase of gait. On each of these links, we fixed these marker plates with 4 markers that we then observed given a known level of measurement noise. And we selected that known measurement noise level to be about 1.5 millimeters, somewhat representative of a well-calibrated optical motion capture system. And then we applied, we were able to simulate this procedure many, many times, given we knew what the true values were. And in each one of these simulations, we compared our least squares optimization estimate to what we could obtain through fitting a probabilistic model and our sort of Bayesian inverse kinematics model. And so if we look at what we sort of produce as results from these 2 approaches, if we consider estimating the angle, the joint angle at the knee, the planar knee joint angle, the true value in our simulation is shown here in green. If we observe one simulation, that being one set of observed markers Y, subject to this measurement noise, this 1.5 millimeters of random error, we apply our optimization routine. In this case, we used global optimization with a hinge constraint at the knee and ankle. And the result is this point estimate that I've highlighted here, this black dot here with a red circle around it. And as I've sort of been emphasizing, this is really all we obtain from an optimization procedure. We have an estimate, but we don't really know what the uncertainty is with respect to that joint angle pertaining from the estimate. However, we have a simulated process here, so we can think about repeating this procedure. So drawing another observation of these kinematics, given this 1.5 millimeters of measurement noise, and we can perform our least squares optimization and obtain another estimate, which happens to be here around 56 degrees. And we can keep doing this. And in fact, we did this about 1,000 times. It's not until we keep performing this simulation procedure, which we can do in simulation, do we get this type of understanding about the uncertainty in our quantity that we're trying to estimate, in this case, our knee joint angle, given the measurement, that level of measurement noise in their system. However, it's important to emphasize that when we do this in practice, we don't really have this ability to simulate many, many times. And so we only really get to observe one of these dots in isolation. So if we compare that to a Bayesian approach or a Bayesian model, the first thing we need to do is define a prior distribution for our unknown parameters. So in this case, I've used an uninformative prior, which gives equal weight to any potential knee angle here. And it's shown here by this dashed blue line. We then observe a set of markers from a single simulation, and we're able to obtain the posterior distribution. And that posterior distribution gives a really rich quantity of information, and that it describes our uncertainty. And so you can see it does a fairly good job of describing that uncertainty that we have, that we can only really realize by simulating this process over and over again if we were to use an optimization type of approach. So from this posterior distribution, we can essentially define any posterior quantity of interest. So we may want a point estimator, and we could consider, say, the posterior mean, the mean of this posterior distribution, that being this thicker blue line down the center here. And then to sort of provide a measure of the uncertainty we have of that estimate, we may consider something like this 95% credible interval that I've shown here or highlighted here in gray. And what this type of analysis shows is that stemming from this 1.5 millimeters of sort of random error in our measurement process, measuring the location of those markers in space, we led to an uncertainty in our planar estimate of knee joint angle that's on the order of about 2.5 degrees. And so we've gained a conceptual understanding of how much we should trust these estimates. Now that's great for considering, say, a single frame of motion capture. But what if we were to, say, consider trying to study, one or multiple gate cycles or a continuous motion in time? And so to see how these two approaches compared in this case, we developed a simulation of gait in that we extracted both the unfiltered marker coordinates from a typical optical motion capture experiment for an individual running on a treadmill. And we derived from these using global optimization a measure of the underlying kinematics. We then smooth these kinematics, similar to if we had previously filtered our marker coordinates in a typical analysis. And we used these as a measure of, say, ground truth. And looking at the difference between this ground truth and these unfiltered marker coordinates, we can establish an estimate of what their measurement noise may be across time. And for a given gait cycle, that tended to range from somewhere between about 2 millimeters upwards to 7.5 millimeters for that single gait cycle. So now we have a simulation of gait where we know the true values, and we can compare our least squares or look at how our Bayesian inverse kinematics approach can handle this type of problem. And the results look a little bit like this. So I'll kind of walk you through these plots. On the top row here, we're examining our knee joint angle, that being the relative difference between our thigh segment and our shank segment. And on the bottom row, we have our ankle joint angle. On the left, I've given you a description of the estimate. So this being the thick blue line, that posterior mean that arises from our posterior distribution as we perform this analysis frame by frame during time. I've also put the 95% credible interval here in dashed lines. And on the right-hand side, I have the width of that interval describing that level of uncertainty throughout the gait cycle. In gray, we've highlighted where stance phase was, where that foot was in contact with the treadmill. And in white, we have what the swing phase of that gait is. And so you can see in general that our estimate, our posterior mean, does a fairly good job of tracking the true values from this simulation, in that, our posterior mean kind of tracks this green line, and this green line, the true values for the simulation are within that 95% credible interval. So giving us some confidence in our procedure here. I've also tried to highlight that uncertainty that our modeling approach, our probabilistic modeling approach, sort of conveys to us in a slightly different format in these inserts, in that these inserts just ascribe a draw from this posterior distribution for each pose parameter, so for our unknown kinematic parameters. And given these, we can essentially draw what this would mean for what the pose of our model would look like given these values. And you can see here at these 2 time points, so during peak knee flexion and roughly during the midpoint of stance, we have different levels of uncertainty, and we can get a bit of a sense about where this uncertainty stems from. For example, we see quite a bit of a fan here at, say, the foot. Again, just a different way to visualize or conceptually understand some of these, the results that this error in measurement has led to us being uncertain in our angular estimate here, our estimates of kinematics. And so just to sort of recap what we've learned so far, in that we've highlighted, and I'm hopefully emphasizing to you that this imperfect measurement system that we have, our optical motion capture system, even though we have quite small random errors on the sort of magnitude of maybe around 1.5 millimeters, this measurement error can lead to considerable uncertainty on the order of 2 to 3 degrees when we're considering plane and joint angle. And in fact, when we looked at the results before, when we applied that across gate, I might just go back a slide, we can see that the uncertainty may be considerably higher than that 2 to 3 degrees, given that when we consider someone in motion here. And hopefully we can start to see the value of taking this probabilistic modeling approach, and that we can start to get a conceptual understanding of what these uncertainties are, and we can start to understand them for the parameters of interest, not just say a residual in terms of a market displacement, or on the scale of millimeters, but on the scale of degrees in terms of our joint angles. But if, like myself, you're somewhat concerned that these estimates look quite unsmooth throughout time, they look quite jagged throughout time, and that I'd suggest doesn't really convey, or it doesn't line up with what we may expect our sort of gate kinematics to be, in that we don't really see a sort of smooth, continuous process throughout time. And this is because up to now we've been solving these optimization approaches or applying this Bayesian model on a frame by frame basis. So we've been considering each frame independently. And inherently that assumes that our marker locations form a series of discrete and independent observations in time, and thus our underlying kinematics are discontinuous in time. I suggest this is probably a pretty poor approximation of what we believe to be the continuous nature underpinning, say, gate mechanics. So, there's a number of solutions we could consider for this problem, the fact that we're getting these sort of discontinuous estimates. At one extreme, we may want to try and incorporate what we believe about the mechanics, the underlying mechanics that are generating this motion. That being, we could consider the inertial properties of our underlying segments of our skeleton that we're trying to model, where the center of mass is, the mass of each of these segments. We could consider how the muscles attached to these segments that result in the motion, or that provide the force to produce that motion. We can consider, say, their moment arms of these muscles and their contractile dynamics, the activation dynamics of these muscles. And we can embed what we know about this process within our understanding of sort of basic mechanics, that being the equations of motion. And as a result, we have this full, quite high fidelity mechanical model of what we believe to be underpinning our gate dynamics. However, if you're familiar with these types of modeling, or this type of modeling, it's certainly quite widely used in the field. These are, end up being quite complex mathematical models, in that they have many, many parameters. They also result in a large system of ordinary differential equations, of which are quite often stiff by nature. And so it's probably quite challenging to fit this type of model from a probabilistic perspective, but I will say it may not be impossible. At the other end of a spectrum, we may consider sort of a statistical approximation to say the solution, the underlying kinematics generated from these mechanical models. And that we may consider modeling our underlying kinematics as having arisen from some sort of smooth functional process in time. And we can incorporate that type of assumption, the smooth function assumption, via the use of a finite basis representation. And we've this is the approach that we applied or have applied to this problem of trying to get a better estimate of these underlying kinematics through a Bayesian inverse kinematics approach, in that we have incorporated B-spline finite basis representations to model elements of our underlying kinematics that we don't believe to be periodic. And conversely, for periodic elements, such as the evolution of our segment angles for a gate cycle, we've modeled those with periodic Fourier basis type of representations. And so you can see that here, essentially, that's all these equations are saying. But conceptually, we can think of these, say that a translation vector, our R here, as being some smooth function. Maybe this is the, say, the translation vector evolving in the X direction throughout time as being a smooth function. And we can model that by a number of basis functions, these being cubic B-splines, and which each have their own parameter associated with them, summing them up, and we can generate this smooth curve in the thick black line at the top. And so when we apply this type of model, we've kind of switched what our unknown parameters are. Initially, our unknowns were, the segment angles and our translations in time. We've now switched these to being the coefficients, these betas, of these finite basis representations. And so we expect by modeling or by incorporating this assumption of smoothness throughout, by using this generalized smoothing approach, will result with a probabilistic estimator that reduces the uncertainty or reduces our posterior uncertainty. We hope that this remains an unbiased estimate of our kinematic process, and thus in turn should reduce the root mean squared error if we were to compare this generalized smoothing type of model to our previous model where we're examining things on a frame by frame basis, this discontinuous time independent type of approach. And that's exactly what we see. So again, on the top, we've got our knee joint angle, and on the bottom, our ankle joint angle. These are displayed on the left as our raw estimate, plus and minus our credible interval over time here on the x-axis. And then on the right-hand side here, we have the width of this credible interval denoting our measure of our uncertainty, given this underlying measurement noise inherent to this measurement process. I've sort of included these inserts here to try and zoom in and make things a little bit clearer, but we do see exactly what we expected. Our estimate coming from our generalized smoothing approach, which is shown in orange here, again, it tracks, as does our blue estimate, our time-independent approach. Both of these track our green true kinematics from our simulated gate example quite well. However, our orange line here could be considered quite smooth, similar in nature to our underlying true kinematics. We can also see on the right-hand side that the width of our credible interval here is considerably less than coming from our generalized smoothing approach than that from this time-independent approach. And this is true not just of stance phase in grey, but also during the swing phase. And this difference is almost more considerable when we have greater uncertainty during sort of faster periods of motion during swing. Just visualizing it another way, we can again extract these samples from our posterior distribution and conceptually get an estimate or get a visualization of what our pose may look like. And we see here, particularly at sort of peak knee angle, that we have quite a fan here, denoting quite a bit of posterior uncertainty if we were to consider a time-independent approach. And this is much less when we consider this generalized smoothing approach. And so as a result, we see considerably less root mean squared error when we look at generalized smoothing compared to a time-independent frame-by-frame estimation of kinematics. Again, in agreement with what we would expect. However, you may notice that at the very edges of of the skate cycle that we've been examining, we see these kind of what are known as edge artifacts. These are quite well understood and and certainly expected from what's known about using, in particular, B-spline bases to model smooth functions. And they result from having only limited information to estimate the smooth function near the sort of the extremes of our measurement period. A sort of practical solution to these edge effects is to simply record more than one stride here and then trim it after we've applied our probabilistic modeling. However, like any approach, any modeling approach, there's a number of limitations that we should consider. And in particular, for the generalized smoothing approach, we see that our results are sensitive to the number of basis functions we use in our finite basis representation of this smooth underlying process. And so we can see that in these plots here, and that we have the root mean squared error of our knee joint angle estimate and our ankle joint estimate, given different numbers of basis functions that we've used to parameterize these smooth functions. And we can see a considerable increase in root mean squared error when we reduce the number of basis functions in our generalized smoothing model from 12 down to 6 in both ankle and knee. And we see a smaller in magnitude, but still an increase in root mean squared error when we increase the number of basis functions from 12 and sort of say double it to 24 or move to 36. Now, for the results that I presented earlier, we were considering basis functions that had a dimension of 12. So we used 12 basis functions to parameterize these smooth functions. This we decided on a priori, so before we examined or fit these models to our simulated data. And we made this decision based on literature that stems well from the 1970s, some sort of fundamental work from David Winter that suggests that any sort of harmonics that we see in our kinematics beyond the sixth harmonic can probably safely be considered as artifacts. And so when we use a basis representation with only 12 functions, and we use a Fourier basis with 12 basis functions to model our kinematics, our angles that we assume to be periodic, then that's essentially what we're doing. We're essentially filtering out and attenuating to zero any harmonics in those angular, those periodic parameters that are greater than the sixth harmonic. However, if we were to improve this approach, there is some uncertainty involved with what the correct number of basis functions is. And in fact, just a determination of this value of k. And so ideally, we could also incorporate how we determine the number of basis functions to use, because this influences what sort of harmonics we end up attenuating or filtering, smoothing out from our underlying kinematic estimates. And so one potential solution to this problem that we're currently considering is to consider a over-parameterized basis, and that we specify a basis with many more basis functions than we expect, but then we include a regularizing term that essentially shrinks higher order basis coefficients to zero, and the rate of this shrinkage is in turn informed by the data that we observe. And so hopefully this makes some strides towards incorporating this determination of how smooth our underlying kinematics should be and the uncertainties involved with that decision within our underlying modeling approach. And I guess this is somewhat in parallel to considering a choice of, say, filter order or cutoff frequencies if we were to consider filtering either our marker trajectories or our process kinematics in sort of an optimization approach that I'm sure many of us are more familiar with. There's also a limitation in that, as we currently have described, within our models, we don't explicitly include non-systematic error terms. So we don't specifically model the effects of soft tissue artifact and how these may be influencing our underlying estimate of kinematics. There have been some approaches in the literature to date that address this problem, such as this one on the right here from Ben Serin that was published just a couple of years ago, and that if we were to consider, say, a rigid cluster of markers attached to a subject, then perhaps this the soft tissue artifact associated with that rigid cluster of markers could be described by some additional rigid body transformation here with its own set of parameters that are different from our underlying kinematics that we're trying to estimate. However, I'd suggest that what data are required for such parameters to be well estimated is still a bit of an open question. In addition, there is the systematic error introduced by having to identify landmarks through palpation, and then identify these with place markers on these landmarks so we can establish our local coordinate systems, and in turn identify sort of where our joint centers are when we collect this data. We haven't explicitly modeled this process within our probabilistic model of how our data is generated, but our lab group has certainly put in some great work here in considering this problem and has developed some awesome tools that can help to perhaps minimize these errors and improve the reliability and the consistency of researchers when we try to identify these landmarks. So that may make some strides towards minimizing these errors. However, obviously an improvement would be to incorporate that sort of unknown process within our probabilistic model. We also have a practical issue in that the way we have evaluated the posterior distribution from our Bayesian models here is through a technique called Markov chain Monte Carlo, or MCMC sampling. What this does is it enables us to draw a dependent sequence of samples from this posterior distribution, and thus, if we draw enough of them, we can capture a good understanding of what that posterior looks like. However, this process is very highly computationally expensive, and we can see that for the single stride that we analyzed in these results, our Bayesian approaches take for upwards of 400 seconds for our time-independent approach, and then our slightly more complicated generalized smoothing, taking upwards of 900 seconds, or in other words, 16 to 17 minutes to get these estimates for a single stride. Certainly many orders of magnitude greater than the seconds it takes to apply least squares optimization. The good news is that there are fast and approximate methods that allow us to evaluate sort of posterior distribution, but being approximate, these have their own set of limitations that need to be explored for this problem. And two examples are provided here, integrated nested Laplace approximation and variational Bayes techniques. These may offer some solutions, but again, we are yet to evaluate the sort of implications of these being approximate methods on our results. Going forward, we've considered just planar problems in this work to date, but we are hoping to generalize this approach to 3D, and there has been some work on this in the literature previously, doing so for a frame-by-frame basis. When we consider trying to incorporate the generalized smoothing approach to 3 dimensions, we have a couple of key decisions that need to be made. One being an appropriate parameterization of what 3D rotation and motion looks like. And so there's a number of parameterizations we can choose from a sequence of Cardan or Euler angles, a finite helical axis representation, or a quaternion representation. And our choice of representation here has implications for what it means to define a smooth process and perhaps a periodic process for 3D motion. And defining smoothness for a 3D motion is in fact quite challenging in and on itself, given the underlying geometry of the vector space in which this SO3 on which 3D rotation lies. There's also a technical problem of coming up with efficient ways of which we can perform Markov chain Monte Carlo sampling on these vector spaces that are these non-Euclidean vector spaces, which we need to sort of pay attention to as we look to generalize this process towards estimation of 3D kinematics. And finally, the ultimate goal for this type of work is that we will be able to incorporate this understanding or this modeling of a single stride within a hierarchical structure. So in general, if we're performing a biomechanical study, we're often interested in, say, the differences between given condition or before and after a given intervention. And to do so, we construct a study in that we collect motion from a number of subjects, and we may collect a number of strides from each subject in our study. The work that I've presented today has been sort of laser focused at just looking at a single stride in isolation from one single subject, and incorporating the fact that we have noise and error in our measurements to uncertainty for the parameters that we estimate for that single stride. Well, as we look to incorporate this modeling process within this type of hierarchical structure, we also hope to be able to incorporate sort of an understanding of within subject variability, so that's between stride variability and between subject variability, which may be of scientific interest if we're to consider ultimately estimating the effects of say, a changing condition or an intervention. And so just to summarize, I hope I've convinced you that the fact that we have imperfect measurements of marker location, we should be very cognizant and hoping and looking towards the future, being able to report uncertainty in the estimates of our kinematics. And so I've shown today that, at sort of a fairly typical 1.5 millimeters of random measurement error can lead to uncertainties when we consider joint angles on the order of between 2 and 3 degrees. And in fact, if we were to consider motion or gait, then these may be considerably larger. I hope to have demonstrated to you the sort of usefulness of considering these types of uncertainties through a probabilistic framework, and the fact that we can use a Bayesian inference type of approach to fit these probabilistic models to successfully quantify and propagate these uncertainties through to the quantities of interest. And hopefully I've shown that model extensions, and in particular this generalized smoothing approach that I presented to you, can help to improve these estimation of our underlying kinematics, and in general does so by creating a better model of the data generating process. And there's many, many more of these extensions that maybe we should be considering or hope to consider in future. So with that, I'd like to thank my supervisors and mentors for guiding me through this work, as well as the funding sources I've received thus far to be able to keep studying these types of problems. And I look forward to the questions and discussion that I know follows these seminars.
At this time, I'd like to encourage the audience members to turn on their video camera if they're comfortable, to allow for a better discussion. To submit a question, you can use the raise hand function on Zoom and I'll call on you. Or if you're unable to do that, you can type your question in the chat box and I'll read it aloud. So I'll maybe start, Andy. Can you talk about what this would look like if this inverse kinematics approach was implemented in Visual 3D besides the current optimization?
Sure. Well, if we can get to the point where we can start, well, if we just to implement it as it is now, I can envision, say a run Bayesian inverse kinematics, a routine button, if you like, and hopefully the output would be a description of this posterior distribution. Right now, to do that, we use this Markov chain Monte Carlo method, in that we draw a large number of samples from this posterior distribution, given that we can't, for this particular problem, get an analytical solution for what that distribution is. And so I can envision, a group of these samples being provided back to the user, of which they could then define the say the posterior mean if they wanted a point estimate, as well as consider the credible interval to get an estimate of the uncertainty and say their joint angles given their modeling assumptions. However, I've thought a little bit about this, how do we go, or should we go about implementing or combining these with existing tools? And at some point, it's great to have something as simple as a push button solution, but there's also a whole heap of assumptions that are, inherently built into these analyses. And, the more we go towards a push button type of solution, then the less a user may be considering these assumptions. And in particular, say, how they'll define their prior distributions and what type of influence that could have. So getting some balance between, a full develop the model on your own and a push button type of approach is something we're thinking about.
Awesome. Thank you. Brent, please go ahead.
Hey, Andy. So I've used some of the least squares inverse kinematics optimizations in OpenSim.
Mm-hmm.
And I would say probably like the majority of people will allow for, when you talk about the kinematic constraints or the joint constraints,
mm-hmm.
they'll allow for flexion extension at the knee, flexion extension at the ankle, and 2, sometimes 3 degrees of freedom at the hip. Mm-hmm. And invariably what ends up happening is if there is any sort of foot abduction or tibial internal rotation and things like that, that has to be taken up by the hip, because it can't be, right, because you don't have the degree of freedom at the knee and the ankle. So I was thinking about this and I was wondering, is that something that's very specific to having a joint constraint in this type of, in an inverse kinematics routine, or would the Bayesian approach give you like not be as sensitive to that as the least squares approach?
Right. So yeah, my understanding is that that type of process is inherent to your choice of joint constraints. And so you can think of that, that choice of constraints is a really important part of your underlying, in this case, say, probabilistic model, if you were to use a Bayesian approach. And so, it's almost like when we say that, we've quantified these uncertainties, it's that we've quantified these uncertainties given our model is kind of an implicit assumption. And so you would probably still see the same, if you want to call them artifacts, but you could also consider, models with lesser constraints and compare the differences, and that may give you a bit more of an understanding.
Okay, thanks. And then, not really a follow-up, different line of questioning. So there's that, that great term, like, don't let perfection get in the way of good enough. Mm-hmm. So you've told me that this very sophisticated Bayesian approach, it does better at telling you what the ground truth is, or predicting what the ground truth is. But are you able to show that it has an influence over a clinical interpretation, whether or not you use just the sort of least squares approach versus the Bayesian approach?
Sure. Well, first off, I hope I didn't convey that it gave a better estimate of the ground truth.
Okay. Because
the point estimate from a posterior distribution in many models, and certainly in simplistic models, if we were to consider, say, just linear regression, for example, we can fit linear regression using Bayesian inference, given priors, and we can fit linear regression using least squares and maximum likelihood estimation. And we will, in most situations, get exactly the same point estimate. And so using Bayesian inference in and of itself does not necessarily guarantee you to get a more accurate estimate. It may do if you have more information that you're incorporating through your prior, etc. But what I hopefully conveyed is that it gives you this sense of uncertainty about what that estimate is, which you're somewhat missing from your optimization approaches.
Yeah, okay.
Now, there was early work that showed that a Bayesian approach may improve the underlying ground truth estimate compared to a least squares optimization type of approach. But our sort of first article here, that we published last year, shows that that's largely due to the choice of prior. And if we consider an uninformative prior, we don't see improvements on quite that level, quite the scale that was originally for.
Yeah. Okay. And then, but the intent, I guess, the intent was, would it matter in a clinical context which approach you use?
Yeah. So if you're just considering the point estimate, not necessarily. But if you wanted to be, rigorous and try to describe the uncertainties and hence your confidence in ultimately if we can incorporate this into a hierarchical model, say, and we're looking at, the difference in conditions or perhaps a pre or post type treatment type of study, whether that's on a single individual or a group of individuals, then if we start to think about this from a probabilistic perspective and start to incorporate this measurement error model, we can start to inherently propagate that error up into uncertainty about what the effective interest may be. And so instead of just considering, say, stride to stride variation or between subject variation as we do now, through sort of an ANOVA type of approach, perhaps if we're considering maybe or a point say peak angles, we'll be able to have this rich understanding of our uncertainties that are inherent given the way that we've estimated or measured these angles given our optical motion capture system.
Okay, thanks.
All right.
I'll read a question from Art from the chat.
Sure.
Why was the root mean square error smallest for 12 basis functions? Shouldn't more basis functions allow for better fits?
Somewhat yes, somewhat no. If we have too many basis functions, then we get to more and more towards fitting our noise. So we get a estimate that is essentially wigglier in nature. So yeah, as we add more and more basis functions, we can, if we had an infinite basis, then we can model any smooth function. And hence we have a very, very flexible object. And the flexibility of that object may start fitting the noise in our system. So if we reduce number of basis functions, given that we used a Fourier basis for periodic elements here, the effect that we're having is attenuating sort of high frequency oscillations in our process. And so in this case, that results in fitting the noise less and a reduction in root mean squared error. Sort of akin to what and there's many parallels between this generalized smoothing approach and say applying a filter. Yeah. Hopefully that answers your question. It's a good one.
Gregor, please go ahead.
Thanks. Yeah, great presentation. I was wondering about, so when you're collecting marker data, typically you have multiple sources of error. One of the error sources is markers, errors in marker position estimations. Another error is, for example, soft tissue movement artifact. Mm-hmm. I can wrap my head around how marker estimates are experience a random noise distribution. What I can't quite wrap my head around is after we do, so assuming that point by point along the time curve, you have a random distribution of your error, surely after the smoothing of the data, a lot of the uncertainty cancels out. Then on top of that, you take multiple estimates on which you calculate some kind of mean, on which you base your analysis of means. So one of my questions is, does it really matter that there is some motion capture based noise to the marker position estimate? And how much does that noise matter with respect to the much bigger influence of soft tissue motion, which presumably is non-random, but rather introduces kind of a bias to the data? I was wondering if you had some comments about that.
Sure. Yeah, a couple of points. So first off, yeah, you're correct. If we were able to repeatedly measure the motion and take averages, then we will, reduce this uncertainty and the error in our measure. I would argue that we can't do that. The only way we could do that is by having multiple measurement systems synchronized in time, measuring motion in time. What we tend to do now is we measure multiple strides and we average across strides. Well, those strides have biological variability to them. And so we start to get this muddling between uncertainty inherent due to the error in our measurement process and biological variability. And often this biological variability is of interest. When it comes to smoothing the data, again, we have uncertainties with our smoothing process. So if we were to filter the data, what cutoff frequencies do you choose? And if you change these cutoff frequencies, well, then we're going to get different smoothness and different answers. And so what I've tried to do with this generalized smoothing approach, it's sort of a way, it's not a filter per se, it tries to incorporate the uncertainty we have in having to smooth our data within this estimation, these uncertainties, they're inherent due to measurement noise. On your questions about soft tissue artifact versus random errors, totally agree, soft tissue artifacts many orders of magnitude larger than perhaps measurement noise. The challenge we have in estimating it is potentially one that stems through identification, in that it's been shown that soft tissue artifacts are on the same, contain the same frequency content as the underlying kinematics of interest in many cases. And so separating these out from any estimation procedure is a challenge. And so hence what listed as a limitation of the approach as it currently stands. But we can think about, if we were to consider a simple model, you could think about data being generalized from, say, a Gaussian distribution with some variance and some mean, mu. But let's say in the case that you want, this mu might be made up of two factors, say a mu1 plus mu2. Well, from an observation of, realized variables from this random distribution, you wouldn't be able to identify what mu1 is versus mu2, because say, if it's mu1 plus mu2, you could, and your ultimate underlying mean was, I don't know, 10, perhaps mu1 is 8 and mu2 is 2, or mu1 is 7 and mu2 is 3, for example. And we have that, I suspect we have that type of problem when we consider soft tissue artifact, in that unless we can incorporate some additional data or some additional modeling assumptions to separate out that are true, to separate out soft tissue artifact from our underlying kinematics, then this is always going to be a potential source of bias for sure. Does that go some way to answering your question?
Yeah, I'm still trying to wrap my head around the connection between the marker motion and the bony motion, which is essentially what we're quantifying. Mm-hmm. And we're using dual fluoroscopy in our lab, and in many situations, the marker motion is nothing like the bone motion. So I find the whole topic fascinating. But how you solve that problem using any type of statistics, that's what I'm uncertain about.
Yeah, and I am equally uncertain about that answer at this stage. But I agree with you, it's a fascinating problem, and one that hopefully we can address in future. I can certainly see it if we can come up with a good model of what that, the implications of that soft tissue artifact looks like. And I mean, there's a few that exist in the literature that range from sort of wobbling mass type of models to a more simplistic approach that I showed here. And so there's some potential to incorporate that type of idea in this approach, but yeah, it does need some further thought.
Thanks.
I have another question, Andy. How do we apply these kinematic uncertainties then to our inverse dynamics?
Yep. Again, something I've thought a bit about. So there's right now the model I've presented. If we were to say take those estimates of, take that posterior distribution and combine it with our ground reaction forces and our segmental masses and that type of thing, then what the result is some sort of probabilistic model that is not necessarily dynamically consistent, in that we have the statistical approximation for angles or translations that's not at all informed by the underlying mechanics. So I think if you wanted to go towards inverse dynamics, it would be pretty critical to consider that early on and to incorporate that as part of your process by which you infer your kinematics. And I know certainly there's some great work. I can think of a paper by Tom van der Bork where he essentially presents an optimization process that, or a least squares optimization routine that also incorporates, say what we know about the inertial properties of our segments to somewhat improve that optimization. So that's potentially one way to do that.
Awesome. Walter, go ahead.
Thanks, Andy. That was very, very interesting. And, I just have probably a very simple question for you, not being in the area. It wasn't clear to me why you have different uncertainties at different phases of the step cycle. And the way I think about it, okay, you have a certain absolute error that's about 1.5 millimeters, and you go frame by frame. Why should that be different in one phase of a step cycle compared to another?
Sure. Part of the reason is motion. And so if these markers are moving quickly, then we get shape distortion. And so identifying the centroid of these markers changes, and that increases the random noise. There's also the fact that motion moves throughout a calibrated volume, and so it's detected by different cameras that may be at different elements of, say, the amount of fisheye in their lens, etc. So all of those things contribute. I will say that the kind of simulated gate example that we presented, and using the residual as a measure of this measurement noise, potentially overestimates this, because it, again, as we've been discussing, it incorporates, say, soft tissue artifacts as well. And while it doesn't necessarily treat those, or it could, there's a risk that it incorporates those as part of this random process. So that may be contributing as well.
Oh, good. The other thing that I was curious about is, I know mathematically, what a smooth function is, but, you talked about smoothness in your movement. So does that ever break down in human movement? So for example, if I looked at a drop jump or something like that, would your technique not be available anymore because you have too quick of changes in the movements potentially, or?
Potentially. So I've considered this a little bit around, well, if we think about, let's look at multiple strides. And so is the point of impact, could we consider that, smooth?
Exactly.
And, we may be able to, and we may not. In some aspects, we could think of, say, coordinated muscle activity as resulting in, smoothing out the kinematics that we observe. However, it may be a better approach to, if we were to use this generalized smoothing approach to, say, inform, say, the mean or the typical kinematics of a given stride, and then model variability around that typical stride. And that variability could come from, differences in periodicity, as well as just, inherent variability of the motion. And that making that type of assumption, so incorporating this generalized smoothing in sort of a hierarchical model, may help to address this, areas that are not smooth. But in principle, we could also include, say, a discontinuity in our underlying smooth function. So we could use a change point model if we wanted to, if we had some, strong ideas about discontinuities that we wanted to incorporate.
Yeah. And the last thing that I was wondering, again, not knowing the technique at all, is, you're showing, running or walking movement, or relative big changes in joint angles, and relatively small errors, 1.5 millimeters. Does this method break down if your error becomes much bigger? You look at other things, you have a very bad conditions for collecting your data, or, or does it not make any difference at all what your error is?
Ideally, it shouldn't make a difference. You'll get an estimate, but we're also getting an estimate of the uncertainty of that estimate. And so if we had an imprecise system, then we would expect that our, say, a credible interval there for our kinematics would be much larger, because our underlying measurement noise was much larger. And so I think this is quite important to consider. It's almost this sort of inverted U of measurement systems, if you like, in that we've made a lot of progress in developing finer and finer scientific instruments for in-lab situations. But now there's some interest in making these even more accessible, lower cost, etc., or moving outside the laboratory. And so perhaps the precision of our instruments is starting to increase. And so quantifying these uncertainties is getting more and more important.
Yeah, in some situations, I'm thinking back about the old days when I used to do human movement analysis, two-dimensional long jumping and so, and there not only did you have uncertainties, but in a situation where you filmed an actual competition, you would only have made, let's say, access of the long jumper or runner from one side, and therefore, arms and legs would sometimes then disappear from view, and then you start estimating where they are and interpolating, and so would your technique be particularly good at kind of estimating the errors that you make there in those type of situations when you lose data because you don't see it?
Yeah, so the generalized smoothing approach can do that, and you can hopefully see the slide here. So here essentially I've taken that that simulated gait motion, and we're in this gray area here. I've occluded all the markers in the system, and because we have this underlying assumption of smoothness and also some periodicity included, we can estimate the kinematics, in this case ankle and knee joint angles, even though all of the markers have been excluded. Obviously, we can't really do this on a frame by frame basis.
Yeah.
Importantly, what we see is that the uncertainty, given that we can't really see our markers, is kind of increased during these periods, as we would hopefully expect. So yeah, there is some potential for that.
Oh, very nice. Thank you.
Yeah, no worries.
Reza, go ahead.
Hey, thank you, Andy. It was a great presentation. I was looking at the uncertainty you got for ankle and knee, and I saw that in ankle you have, after smoothing, you have a huge reduction. And then in finding the number of basis function, you decided to choose 12 as the function that produces the least error. But I saw that just 4 simulations were performed there. So if we increase the simulation, how certain are you to say that, okay, might be the value might be 11, not 12, the local minimum?
Yeah, exactly. So those plots, I was just trying to make the point, I guess, that our answers currently are sensitive to that choice of K, that choice of the number of basis functions. And I mean, not by design, it just happened to be that 12 seemed to give, of those 4 that examined, give the fairly good, or gave the lowest root mean squared error. But I wouldn't say we're confident at all that 12 is the best number to choose. That's why in future I talked about coming up with a model, and that we sort of over parameterize our basis, and then we put regularization on it. And the idea is that by doing that, we're including this uncertainty in this process of, hey, how many basis functions do I choose? We're including the uncertainty in our estimates, and we're trying to inform that decision from the data we've observed. And as a result, our results don't become sensitive in the way they are currently. And so I guess as a parallel, you can think about that being a way to, if we were to try and include the parameters of a filtering of either marker trajectories or process kinematics in developing our ultimate sort of estimates.
Okay, so to find that number of basis function, do you have to run the simulation for all the functions, the number of basis functions?
To produce the results in the talk today, yeah, I did. But again, in principle, in this sort of future approach that we're exploring now, if you had this over parameterized situation with regularization, no, you don't have to keep running the simulation. Those are parameters within the model.
Oh, nice. Yeah, awesome.
Other questions from the audience? I'm going to read another question from Art in the chat box. I guess your RMSE is calculated respect to ground truth rather than data. I have two problems with that. Art does, not me. First, ground truth is generally unknown to us, and so shouldn't this be called Andy's truth? Second, your Bayesian estimation also doesn't know the ground truth. So is it fair to grade it against something it never knew it was being compared against?
Sure. So we used root mean squared error because we simulated and hence knew ground truth. So it is, yeah, it's a root mean squared error against the ground truth, to answer the first part of your question there. If we think about root mean squared error, and if we ignore the root bit and we just consider a mean squared error, then we can derive mean squared error as a combination of bias and variance. And so in doing this, taking the root just puts it on the same scale as what we're measuring. And so by doing this, we're essentially evaluating how good our statistical procedure is, and that we're evaluating, if we have a statistical procedure with lots of bias and say small variance, then we get large, or if we have a statistical model with lots of bias and lots of variance, then we get a very high root mean squared error. And similarly, we could have models that have, say, less variance but some bias, etc., and we can trade off these things that way. So, yep, totally agree. Ground truth isn't known, and hence why we use simulation to evaluate these models and use root mean square error to compare between these two statistical models. Just reading the second part of your question again. So, Bayesian estimation doesn't know the ground truth. To completely agree. So, is it fair to grade it against something it never knew it was going to be compared against? Again, we're trying to show that this model is capable of measuring what we're or of estimating what we're pretending or what we're attempting to. Hence, using these simulations. And again, that's why we used this simulation and hence root mean squared based on the true values of the simulation. Whether it's reasonable to use root mean squared error as a metric, and shouldn't the goal be to reduce Bayesian uncertainty? Well, we could think of a model and that has a very narrow credible interval, i.e. doesn't have much uncertainty but is biased, i.e. there is some offset from the true values if we were to, by some divine intervention, be able to tell what those were. And so that, I would argue, is a poor model. And so getting this balance between bias and variance or uncertainty is important, and that's why we're considering root mean squared error.
Great. Other questions? Awesome. I don't see any other questions, but if anybody has any other, I hope you follow up with Andy after the seminar. Thank you, Andy, for your great presentation today, and thank you to all the audience members for their questions. Next week, we'll be hearing from Gregor Kuntz, and his presentation title is Cerebral Palsy Gait Biomechanics, Everything But the Kitchen Sink. So I hope to see everyone again next week, and thank you for joining.